So we're already 5 minutes past the beginning of this presentation. So let's take a seat and we'll start right away. Okay. So the subject, I'm not going to present myself a second time, so I'll just keep going. The subject today, we're going to talk about DMA Fences in GStreamer. DMA Fences is a new feature that got merged into the Linux kernel recently. And it opens up a new paradigm for exchanging memory between components, well, hardware in this case, but it could go further. So we'll go over what's a DMA fence, what it can be used for, and what it is used for, in fact, and what's the limitation for us in multimedia. So I'm really speaking from a multimedia point of view, and how we could actually make use of these feature in GStreamer. Um, it's the first time that I'm actually making a talk on something I'm not writing. I'm not on any fixed design. I'm basically starting to think about how we're going to go forward with this new mechanism. So there's nothing here that is fixed. It's all open for discussion. It's ideas. So feel free to contribute. So my usual little definition. So basically, it's a mechanism to track asynchronous operation on a buffer. I've taken that actually from OpenGL specification. That's exactly what it is. You ask your system to do something on a separate coprocessor, and this object will let you actually figure out when that operation is done, actually, to synchronize with the termination of that operation. In Linux, everything is a file descriptor, so yet the DMA fence is a file descriptor. It's so if you have a DMA buff that is exported with a fence, you actually have two file descriptors. So it's associated, attached to a DMA buff, but not really directly. But there's a link between them at the driver level. The fence is actually a signaling mechanism. You can poll it, you can select on it, and it will tell you when the content of the DMA buff is fully written. All the fence can be merged together, actually, if you want to wait for multiple buffers to be ready. On the kernel side, that's what it looks like. So the little API there, that's actually the Android API, but it's easier to read. And I've put in smaller the kernel API associated to it, which is not as easy to read. So usually we wrap these into an API. That's what Android did. So sync wait with a timeout, let you wait until you reach a timeout actually for the fence actually to switch to the next state. A fence actually has three states: the not signal, signal, and error. So that's why I say state and not just when it's fully written. You need to then, you can actually, if you want, merge two or more. You just need to call successively this function in order to obtain like what we call a sync file. And this is a new FD, yet a new file descriptor, which will actually track multiple file descriptor. And you can always do sync fence info, and I'm missing one which is recent, so it was not in my slide, which is I think it's sync fence file info, and that gives you actually, oh no, it's file info. I put the okay, I put the new IOCTL in the old function, but it gives you actually the list of all the fences in that is being merged. And for each fences, you get the status, the timestamp of the last state change, and I think there's some counter in there. I got a blank, but mostly it. So it's a mostly trivial API to use. I give you a buffer, I give you a fence. You can carry the buffer around, you can do some setup. And at some point, if you need the data, you can wait on the fence. The data is ready, you're going to be able to use it immediately without a context switch. There's the notion of in fence and out fences that is everywhere in the documentation and in people discussion when they speak about that. I think it's important to understand. It has nothing to do with the direction of the data flow because this is not for streaming initially. It's just that an in fence is the fence that you pass to the kernel, and the out fence is a fence that comes from the kernel and is giving back to user space. It's just useful knowledge if you want to understand the discussion around. So, what can it be used for? The idea of a fence is that, and here I start with my multimedia pipeline. A theoretical source could give me a buffer and a fence. It will say, instead of saying, here's a buffer with an image in it, it's here the buffer, I'll put an image in it. So it's a future action. And here's the fence that will let you synchronize with that. Immediately, I can take that buffer, give it to the GPU. GPU is happy. And in return, he's going to give me a new fence with a new buffer, the result, that I can give immediately to the display. I still didn't capture anything. I still don't have data. But everything is set up. And as soon as the buffer is produced here, it wakes up the GPU that does its processing. It wakes up the display that also does its processing. It's fully automated. You could see that as similar to what they wanted to do in OMX, the OMX tunneling method. So you got a bit less control after your setup. It's difficult to stop anything from happening there. But the user space is not in a way. You don't need to wake up the user space every time. So same thing here, but I've translated it quickly on what looks like a timeline. So these are time periods going from left to right. If you look at what we do right now, we would actually get the capture driver doing his work, delivering the GPU, which will do his work, and then back to user space, and then we'll pass that to the display. So there's multiple context switches and transition between the kernel and user space in order to bring your frame to the display. With the fences, what happens is that you do all your setup, all drivers ready, and then everything's happened in a go. So you get actually the theoretical maximum throughput. Currently, drivers, especially drivers of the same family, they go further than that. They negotiate through the fence type with special API, the ability to transfer parcels. And I'm using the term parcels, not slice, not lines, not tiles, because there's a wide variety of type of parcel in the field. It's really like each engineer with their own hardware, they try to find the best way to transfer the information. And it's quite close to signal-based drivers, but it's not signal-based in the sense that it's not a physical line. It's actually going through memory in between. So it's like getting closer to a signal, but with memory buffers. So what's the benefit? You get less user space context switches. You got better hardware operation in your pipeline. So you keep your user space out of the way, especially that you don't really run GStreamer on an RT scheduler, so you don't have much priority. So if something else needed CPU when one buffer was ready, you could actually delay submission, and that delay is extra latency, and it's variable, and we really don't like things that varies. That's one of the biggest issue, and it also allow for specialized hardware negotiation of latency, of transfer, of parcel transfer for lower latency. So that was the easy part. Limitation, that's relatively short. It's specific to the multimedia domain. So the problem with that is that, if you have a camera, you want a hardware timestamp of when that image was turned from light to a buffer. And the way that it's being delivered, we got just no idea, basically. So if you want to do capture with the DMA Fence, you need to sacrifice the hardware timestamp. In fact, driver could go further because they can predict when that's going to happen because they know the clock setup. They know a lot about their camera. But that's not true for a USB camera, which is a foreign hardware sending you frames. So it means that the perfectness of your time synchronization might be harder to achieve actually with the fence. It's also pretty hard to use a fence with a display and be able to introduce a delay. So in multimedia, yes, you could go as fast as possible and get the frame to screen, but in fact, you need to wait a little bit. So when you display that frame, it matches the audio samples. So you get the proper lip sync. And if you pre-queue, especially with the way the Linux DRM system works, you cannot have there's no queue of buffer of operation. There's no planned timestamp. There's no timeline where you say, hey, do that at that moment. So right now it's quite limited. So most likely the capture and the display, they're not going to do that. So you would use that in a GL element. You would use that when you speak to your GPU, to your FPGA program, to your CUDA program. But it's for display, for synchronization, it's still quite limited. We'll need more kernel API really to get there in the multimedia domain. And now comes to the experimental part. It's like, so what's our option using what exists in GStreamer to actually get that running? First spin, I thought that maybe we could go simple. Use the allocation query, set a meta API, just like we do with composition meta, with the existing actually GL fences. So we already have in GStreamer a fence mechanism in GL, which is used actually to synchronize the asynchronous transfer of data from one GL context to the other GL context. Same thing, it's the same pattern, but it's a GL fence, it's a different mechanism. So allocation query gives you the ability to pass back a meta that says, oh, I support that. And then upstream can say, okay, I don't need to, I have a kernel that gives me fences, but I don't need to wait on fences before pushing buffer. I can just send that. And I could attach the DMA fences. I could create, as an example, a DMA fence meta and attach that to the buffer and push it downstream with the assumption that because downstream supports that, it's going to work. Now, that is the idea. And then, oops, that's up. Just flip to. Now, but it's weird because it's supposed to be attached to a DMA buff, and then DMA buff is not a GST buffer; it's a GST memory. So maybe it would fit better on a GST memory, but then we need a mechanism to be able to attach something to a GST memory that does not exist. Other question, well, the GST GL fences are nice, but as soon as you put the T, they stop working. It's a bug that we need to address. Currently, the reason is that as soon as you're done waiting on a fence, you destroy that fence. So if you have a T, 2 branches, the first branch that is done waiting will destroy the fence and crash the other side. So is it a design error or is it because we use meta? We need to analyze this and figure it out. Also, how do we make sure that in-place meta are aware of that? And the answer is that, well, there's no way other than a caps filter like we do for composition meta, crop meta, etc. If you don't use a caps filter, and in between actually in-place filter, like let's say you would do a color transform, but in the same buffer, it means that you actually proxy the allocation query. So in theory, the thing gets negotiated. But you don't want that because it means that you're going to do an operation on an empty buffer or an half-written buffer. It's not correct. So that brings us to using a caps feature. But if we're going to use a caps feature, maybe we should just try and start thinking at implementing a completely new way. Just as I said in my previous presentation, caps feature gives you the opportunity to define new rules. And we're actually in a new paradigm. We have a new way of streaming buffers in here. And we could actually just embark into that boat. And I'm not saying this is the way to go. I'm just thinking out loud. We could go further. Oh, that's a. We could actually go further and start thinking of what if we actually add a fencing mechanism globally in GStreamer? Because a fence doesn't have to be hardware driven. You could easily implement fence protocols to transfer parcel of data between one element to another element. I'll give you right away an example. There's an encoder that we do support now. It's called OpenH264. And it actually supports receiving slices of images and processing and starting the process actually of that slice of image immediately as soon as it arrives. You could say, okay, we'll wrap this into GST buffer. But as soon as the amount of parcel will become significant, like as soon as your parcel will be something like Pipewire is doing, 32 bytes, things will start to blow up because for every time you're going to take locks and, you know, this is going to be like too much overhead for the amount of data that you're passing. You'll have as much data as you have metadata with it in terms of memory space. So just opening the idea. So we could start to add special API in the DMA buff allocator, or we could even go further and start adding special API in the memory allocator, and then really have a meta that represents a different way of exchanging buffers. So the buffers is just a container, and then there's an extra signaling for the rest. So that's it. Maybe we could integrate fences, not DMA fences, but fences in general. And then the DMA fences become just a subset. And same thing for the GL fences. And we could actually solve that problem in GL in a solid and extensible way. The rest I already said. And that's it. Some conclusion, and I actually got more than that. Was a bit late on the slides. But yeah, DMA fences are clearly designed for GPUs in the case that you already know your metadata. And it really doesn't fit in GStreamer to asynchronously transport metadata like timestamp. It would break a lot of things, including all the nice tracers that we're implementing, because they very often look at this information. Another thing is that currently the DMA fences, they don't allow any type of user space interaction. So let's say you have a USB camera and you want actually to get the data from the USB camera. The camera will capture quite quickly into its own RAM, and then it will transfer over a relatively slow speed USB wire. And the fact is that it comes in order. So especially if you look at our new video convert threading model, you could start actually feeding your conversion thread as soon as it gets in. So you could get the full buffer, and you could get from the kernel the information that, hey, there's 20 lines ready. And then we could pass that in our software converter, and we could save a lot of time because we start processing early. There's no support for any of this in the network stack at the moment. It would be quite convenient to be able to get out of the way when you want to do high bitrate transfer. They can greatly improve the efficiency. So you really get your user space out of the way. So your user space becomes a controller, just like a driver would be. So it's about setting up the operation. And it's not only your user space, maybe I missed something here. It's also your streaming thread becomes like out of the way. Because if you have a software elements that do multi-threading, or that do multi-GPU core threading or something like that, you can actually, as we go, schedule the work as it comes. and you'll get to the end of that work much quicker. And then you can chain that to another element that knows that in which you negotiate that parcel transfer. So basically, we need to come up with we need to analyze and research about what's those parcels and what parcel protocol we need to implement actually to get going. It's really that. So yeah, and clearly, if we go ahead and we go forward with that, just thinking of the GST Shark presentation. So they had a pipeline. First element was taking 25 milliseconds. Second element was taking 25 milliseconds. That's 50 milliseconds. So that's too slow. Their solution, they added a queue. So they added a thread. But let's assume these two elements could provide you parcels and you enable fences between those two parcels. Well, you're solving the same problem at a parcel level without introducing a new thread. It's quite interesting because I mean the multiplication of threads in GStreamer is a big issue. It's really, I mean, we use a ridiculously high amount of threads when we build a GStreamer pipeline. So when your solution is to add a queue, well, it's also to add one more thread, and most of our threads do nothing. That's it. That's all I had today. I'd like to get your questions. So, no questions? Go ahead. So the question is if I have an idea of what would be the best implementation. To be honest, I only been thinking about this for a month or so. It's gonna take a couple of months, and I'll come back on that. It's I need to first prove this concept. So I'll probably write something non-GStreamer to figure it out. And the other concern I have is that GStreamer is already very complex. So if we just add yet a new way of exchanging buffers, maybe we're just piling up. So that's why it's a project, it's an idea. But meanwhile, we'll still have to pass the hardware fences because that's where the driver is going. And we could synchronize immediately, but we're not improving efficiency in this case. Go ahead. So he's asking if creating like partitions, having different, like all having OpenGL, having this concept to start with, and just moving all the OpenGL to that concept would work better. I think it's kind of already the case, just that the implementation needs some help. Right now, it works. I mean, the fence implementation in OpenGL is in all of our OpenGL elements. It's really about you wait when you switch contexts, which only happens between like your pipeline and an external sync, like GTK sync, the Qt sync. Well, the WebKit browser now is using that, so that's where you actually wait for the fence. And until we fixed the the allocation query in the T, we didn't know it was broken for multi-branches and multiplexing. So in theory, it's already implemented in GL. We don't make a very high use of it, and GL doesn't give you parcel access to any parcels, so there's no way we could go further. Yes. So the question is, how would synchronization be a problem? So the problem of synchronization is first you need the timestamp to do proper synchronization. Otherwise, it's just a guess. And the problem, in fact, is because as soon as you queued an operation, it's queued. And it's really unpredictable at this point when it's going to happen, because the driver is no longer rendering anything. I mean, it keeps the old one, reft, for redraws, but it's not rendering anything until the fence trigger. And normally in multimedia, we can cancel stuff. We can do QoS, we can drop it. Right now, there's just nothing. There's no API, there's no evidence. And let's assume that it got canceled. Well, it's going to error out. But for that, you need to pull the fence. We're out of thread also in the sync element. So does it mean that to handle fences, we'll need a thread in all our sync element? And yeah, I had another thought to that maybe eventually we need a polling service in GStreamer to stop creating threads that only poll file descriptor to give us events. Another thought, but that's really another project. Well, thank you very much. Enjoy your day.